Okay, let's work this ice skater example. It's a good angular momentum problem, and it's always kind of a typical real-world example of conservation of angular momentum. And so basically in this problem we have an ice skater whose arms are extended, and she pulls her arms in, and we're asked to calculate what her new velocity is. Okay, so anytime you have some object's moment of inertia change, angular momentum has to be conserved. And so when her arms are extended, that's going to be her initial moment of inertia. We're told that's 2.34 kilogram meters squared. And her final angular momentum, that is when her arms are pulled in tight, is 0.363 kilogram meters squared. Okay? And her initial angular velocity is 0.8 revolutions per second. And we'll keep it in revolutions per second for this problem. It just means that our final answer is going to be in revolutions per second. Okay? And conservation of the angular momentum tells us that the initial moment of inertia times the initial angular velocity is equal to our final moment of inertia times final angular velocity. Okay? Now if we divide both sides of this equation by our final moment of inertia, we see that the angular velocity in the final situation is equal to the initial moment of inertia divided by the final moment of inertia times the initial angular velocity. Okay? So we can plug these values in now. Initial moment of inertia is 2.34. Final moment of inertia is 0.363. And our initial angular velocity is 0.8 revs per second. Okay? So you do this calculation, and the number you get for the final angular velocity of a skater is considerably larger than when it started, 5.16 revs per second. Okay? So again, considerably larger than our initial 0.8 revs per second. So and this is with no extra pushing on the ice by her skates. She's just spinning and pulls her arms in. And we'll see a good demo of this in one of our upcoming class meetings.